In this video, we present a demo of use case 13, secure industrial communications. We have 4 partners in this use case: Westermo AB, Rice Research Institute of Sweden, TietoEvry, and Malardalen University. You can see here high-level architecture of use case, including our virtual environment or physical environment that we use to collect the data resources, or components that we will design within this use case. On top of these 2 environments, including the intrusion detection systems, attack modeling components, analytics, mitigation, virtualization systems, and penetration testing, that these components will be run on the edge or on the cloud, depends on the need. What you see next is a presentation of cybersecurity testing for industrial control systems. And then we also show what we have done so far to design AI-based intrusion detection that will be later also added to this virtual environment.
In this video, I want to present the ICSIM testbed. The ICSIM only covers the first 3 layers needed for our intrusion detection methods. ICSIM is a framework that can simulate an entire control system. We have used Python language to use wide range of shell components. The framework have all base classes for DCS components such as PLCs, HMIs, protocols, and hardware simulation. Testbed components are runnable containers, which are compatible with GNS3 network simulator or Docker container technology. To be more realistic, this framework supports different types of industrial network protocols, such as Modbus or Ethernet IP. This framework has a component for running different types of attacks, such as DDoS or man-in-the-middle. ICSIM use EtherCAP to implement these attacks. ICSIM also contains base classes which use Wireshark to generate a dataset of normal and under-attack behavior of the system. There are also classes to develop intrusion detection systems using AI, ML, and digital twin. First version of ICSIM have developed with implementing main components, such as simulated process, HMIs, PLCs, logics, and Modbus protocol, which are highlighted in this picture. We have decided to leave some other details for the next versions. Now it's time to run a demo. The demo process is a simulation of bottle filling factory problem. A water tank provides water for filling bottle on the conveyor belt. There are 3 actuators: the tank input valve, output valve, and conveyor belt. Also, there are 4 sensors which measure tank level, bottle level, pipe flow, and the distance of the next bottle to the filler. Based on the max and the mean threshold of the tank, system close and open the tank input valve. Meanwhile, system try to fill bottles, and then conveyor belt move the bottles to replace the filled one with the new one. This is GNS3 environment, and I created the bottle filling process using ICSIM. We can run all components by click on the start button. We have used customized Westermo switch, which is currently up and running. We could also see that PLCs are running. HMI1 shows the state of the system. Tank input valve is currently off and it's operating on the auto mode. Tank level has a value of 3.7, which means that the control system was able to maintain its level between 3 and 7. HMI2 can send commands to modify controllers, such as changing set points or forcing the state to the actuators.
As you can see here, we use a pre-existing dataset. First, we started with some feature selection or reduction, depending on the method. We use 2 of them, correlation coefficient method using Pearson, CCM, which is a feature selection to decide which features to use and which one to not use. And then we have also applied principal component analysis, which will do a feature reduction. After applying one of these 2 methods or none of these methods, we will use a classification algorithm, which can be artificial neural network, long short-term memory network, or random forest. Here we can see the results from the 3 different algorithms. We can see that all of them got better results using CCM as the feature selection method, but the differences are not so big. And then we applied all the different algorithms together. We got what we call DST, and we improved the percentage by 1.5%, getting a total of 88.5.
At TietoEvry, we have developed some machine learning lifecycle management framework on the cloud and on the edge. And here it's a presentation of this framework on the edge. A quick demo. Here we can see how data versioning is handled, and then different experiments which have been run, and we can monitor them with this list and different graph and explaining the different accuracy of the different model. And then when we have a list of models, we can select the right one manually or automatically the latest one who has been generated. In the end, we can also specify where to deploy those models, and also testing them with some vanilla example.